Jaime Rios. I'm a junior here at the university. I will be doing research in the vein of additive manufacturing pretty much all the time. So this is the world that I know. This is also my hobby. I am by no means an expert, but I have a lot of practical experience and time on our printers, and I'm going to share with you today what I know. I hope that if you get really interested in it, you'll spend a lot of time downstairs in my lab, and I'll be happy to share with you whatever we're working on and whatever I've learned there too. So what we're going to talk about today is additive manufacturing kind of in general, and then we're going to switch to specifically additive manufacturing on the platforms we have available to us here at UDC. So just a quick overview of what we're going to look at today. Obviously nobody wants to sit through a 3-hour class straight through. I don't want to talk for 3 hours straight through, so we're going to break it up into a couple of parts today. If one of the parts is not something you're interested in, you're not going to hurt my feelings if you take one or take the other and don't stay for all of them. The first part, what we're going to do here to begin with, is we're going to do an overarching talk about what exactly additive manufacturing is, what it can and can't do, and when to use one platform versus the other. We'll take a little break after any questions anybody has. For this part, if you're the kind of person who's taking notes, I will make this presentation available to everybody after this. You won't really need a lot of notes here for this first part. The second part, we're going to talk about prepping files. We're going to get much more specific in the second and third parts. So if you are interested in using the print platforms here that we have available, the second and third parts are where you should probably start taking notes. I have some stuff in here, but in there we're going to go through an actual demonstration of how to use Cura, how to use Chai2Box, and how to prepare the files from Creo for those softwares. Once we have that set up, we're going to slice an actual file for one of the printers we have available so you can see how it works. Then we'll take a little break, and in the third session we'll actually go back here and we'll talk about the specific printers that we have available, how to set them up, how to know when something's wrong, what not to touch, that's equally important, and how to get give yourself the best chance of having a successful print. Because it's not as easy as just clicking print on like a Xerox machine. It doesn't really work that way. So let's get into it. What is traditional manufacturing? Well, traditional manufacturing starts with a large piece of stock and goes down to the geometry it needs. We call this subtractive manufacturing. I forgot to turn the music up there, sorry. So the problem with traditional manufacturing is that it's wasteful. According to studies done at NIST, actually, subtractive manufacturing, and you can see here, they started with a solid block and now we're down to just the guitar there. This wastes about 60% of your material if you get it correct the first time. If that table gets bumped, if you lose a drill bit, if part of the wood cracks, the whole thing is wasted. It's worthless. You have to start over with a larger piece of stock. There's a couple of problems that come inherent with this type of manufacturing. The first is you have a very limited set of geometries available to you. You cannot carve a hollow block. You cannot carve things that are in perfect flowing, swoops and flows unless you use computer-aided machinery. The vast majority of this type of work is time-consuming and takes much longer than additive manufacturing. Not to mention the fact that it requires people who have been trained in how to use the CNC, can set the file up. The files have to be created correctly in CAD first. And the fact that you have to do it by hand means that we're running out of those people. Millwrights, welders, trades craftsmen are not things we're producing anymore. The time when a guy who had been a welder or a millwright for 50 years and could tell you how to do every little thing is over. They're just not being created anymore. And the ones that are being created will take another 50 years to develop that level of expertise. Your other problem is it's a prohibitive upfront cost. Say you're going to make that guitar. When you design it, you have to pay for the stock, you have to pay for the millwright, you have to pay for the time on the CNC. on the hope that your design was correct the first time. If it's not correct, you have to refigure your design and pay for all of that again. That's an extremely prohibitive upfront cost for a small business who's trying to make a first prototype. So what is additive manufacturing? Well, additive manufacturing is kind of the all-encompassing term for what we commonly call 3D printing. Additive manufacturing is the opposite of traditional manufacturing in that we don't cut away from a larger block, we build up the exact geometry we need. There is zero waste in the product because we only use the amount of product required to create whatever model we have. Now, it comes in several flavors. We're going to focus today on the 3 specific variations that are available to us here. That's the fusion deposit modeling. That's the kind that most people think of. That's the plastic printer. There's SLA, which is stereolithography. That's resin printing. It's fairly new. We also have that just now available to us. And there's the direct laser metal sinter. I'm not sure how many of you have ever seen it, but on the 3rd floor and behind the red doors with the giant warning signs, that's a metal 3D printer. That's direct laser metal sinter. That one is not readily available to everyone, and we'll talk about why here in a little bit. So fusion deposit deposition modeling. The material comes through in the form of a filament and is melted in the hot end and laid down in specific patterns over and over again, building it up until the full geometry. This is a time-lapsed video. This is nowhere near the real print speed. In reality, it takes quite a while to print one model, generally at a high level of resolution. FDM, however, is typically, of the 3 platforms we have available, is the fastest. It is always the cheapest. And it works in a way that allows you to have a structurally sound material but still be hollow inside. So it's the most cost effective no matter which way you do it. The problem with FDM, the drawback, is that it's not very structurally strong. Because of the way it works, we lay down stratas and build them up. But we can't completely fuse those things together. So you have stratified layers. From this direction, it has much more strength than from this direction on the side. It'll split at one of the layers very easily. So this is best used for rapid prototyping, proof of concepts, and things that are not going to have much stress or strain on them. Toys, add-ons, pin holders, desktop things, you know, simple things. Stereolithography is the newest addition to our printing platforms here at the university. Stereolithography works by having a vat of resin, photosensitive resin. The resin is cured from the bottom up. So underneath this tank, which is full of liquid, the bottom is clear. You can see here there's an LCD screen which shines a light in a specific pattern underneath it. That pattern cures the resin that it hits right there in that area. The plate moves up just a little bit and it does it again. Instead of a path of G-code like the plastic printer uses, this actually uses a series of photo images that it continuously shines the light. We have a time-lapse video here. This also is much speeded up. Of the 3, this is one of the slower ways to print things. The advantage of stereolithography is the wide range of resins we have available to us. So look, this is my favorite one because it looks like magic. It looks like it just pulled it right out of that liquid tank. It's just so awesome. The resins come in all kinds of varieties. The cheap resins that we buy off of Amazon right now to do research are just plain photopolymer resins. They cost about $32 a liter, and those liters last us. We have printed every day on that printer since we've got it, and we have only just run out of resin. However, with a little more cost, you can get resins that are high heat. We have a sample downstairs that can go up to 236 degrees before you see any deflection in the material. They also have resins that are high strength, ceramic resins that can be fired in an oven. There are FDA approved resins that can be used for medical devices once they're sterilized. I don't know how many of you have seen on TV those Invisalign braces, they're the little plastic trays instead of braces. Those are printed on the same machine that we have here available to us. It's right out of the machine, it's ready to go. They're also, in some of the samples I'm going to show you here in a minute, being used for parts for mechanical hearts, parts for catheter interfaces, and parts for devices that need to be flexible in some areas and strong in some areas. They're very versatile printers. These printers are best used for materials that are going to be smaller in size because build volume is an issue. That's a limit for SLA. The materials that need to be strong, that need to be precisely detailed. This is a very high detailed print. And materials that need to be need to carry medium to low end stress loads. You really can't lean on a resin too hard, but you can on some of the stronger ones. Finally, here at UDC we have the direct laser metal sintering. This is a video, also super high time lapse. It is a very slow process. What happens is you'll see it come across here again with the arm. The arm lays a microns thick layer of powdered metal. Then the laser will shine in a specific pattern. The area that the laser hits fuses the metal together, essentially welding it into a solid piece. It builds by micron layers up, and when the thing is done, you can take it out. I'm oversimplifying, but shake the dust off and you have a fused metal piece. Some of the drawbacks of this are it's extremely dangerous. To be in that room, you have to wear level 4 PPE. For those of you who don't know what that means a full face respirator. When we change the condensation tank of the machine, we have to wear a full suit and respirator because the condensation is flammable and explosive. If you get this powdered metal in your lungs, it's very bad for you, and it's very easy to do because it is a powder, a fine powder. The way they make it is they take the exact what you think it happens. They take a bar of 316L, they pulverize it into a powder, put it in a kilogram jar, and give it to us. The advantages of DLMS is that you can create fully castable metal parts straight from a virtual model. Now, for those of you who don't have a manufacturing background, that's revolutionary. Because in the past, traditional manufacturing, I created in a week in our printer a 3D printed heat exchanger made from stainless steel. In the past, if you wanted to do that, what you'd have to do is make a mechanical drawing, which means you could design it virtually, but you'd have to get a full mechanical drawing. You'd have to take that mechanical drawing to a millwright. He would make your prototype by hand. You would take that prototype, you would put it back in your system and see if it fits. It never fits, so you take it back to him, and he takes some corner off here, takes some corner off there. Then you take it back and see if it fits. And almost never the second time either. You do that over and over and over again. On average, you're looking at about 3 to 7, 10 months, somewhere in that range, before you have a workable part. Now the problem that comes next is you're not making that one part like that. That's way too expensive. The only reason you do that is because you're going to cast that part for $1 million. I made it in a week with this machine. I made it an hour virtually, put it in the machine, let it print, we took it off the platform and put it right into work. That's revolutionary. Think of what that means for auto manufacturers, what that means for civil engineering models, what that means for people who are designing prosthesis and first run parts that have never been designed before. You can take it down to a series of hours instead of months and weeks. And you can take it down to about $400 cost instead of $100,000 cost. So some of the current uses, like I talked about already, aerospace really wants this. They want it for a number of reasons, but the main reason they want it is because currently turbines are made by hand, by very skilled workers. The turbines that spin in the giant jet engines. What they would like to do is take that 50 years of knowledge that currently makes that by hand and bring it over into additive manufacturing and be able to print those turbines right out of the machine ready to go. The problem with that currently is the surface roughness of a printed part is much too high to use in a precision engine. So that's where the current research is on that. The construction industry is already really taking to this. If you've never seen it, I'll show you here in a minute. There are 3D printers that print in concrete and can create a house. You can leave this machine in a field and come back in 4 days and have a completed house. That is revolutionary. Let me tell you who really wants that. The nation of China is extremely interested in that to help with their low-income housing crisis. So imagine what that would mean to not have to have a construction company go through permits, blah, 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 and take 5 months to build a house when you could leave a machine there and come back in 2 days and move the machine over and make the next one and the next one. It's incredible. The toy industry, of course, is all over it because prototyping toys is expensive and toys are cheap and you don't get a big return on your value. If you can make one toy in this machine, make a mold of it, bust out 100,000 of them right away in a week, that's a great plus. Automotive industry, the food industry, I don't have a video of it because I couldn't find it, but if you can get some time, in Japan, chefs are using 3D printed platforms that make chocolate sculptures, that make sushi that is in incredible pieces of art. I wouldn't eat it, it's just beautiful what they can make. So pretty much, this is the way I describe additive manufacturing to people. You remember when you were a kid and you were sitting at your house, looking around your house, and you said, man, you know what would be cool? And then the rest of that sentence was something that nobody was ever going to make for you because it was going to cost $100,000 to make. That's what additive manufacturing is. You know what would be cool? I'm going to go design it on my computer and print it out on that machine because I want it, for no other reason, because it cost me about 12 cents of plastic and about an hour of my life to make it. And that's what additive manufacturing really should be looked at as. The open source, just designed for anything in the world. So some of the ways that it's being used that are my really favorite things. Because of where I am and what I'm going to be working on, these are my two favorite stories about 3D printing right here. This is, right here, a 3D printed jet nozzle that will be used on one of the Virgin Galactic spaceships. They 3D printed the design in a smaller version and put it in their lab to test the propulsion level of the nozzle. The reason that's so important is because they did it in a weekend. The design had been virtual already. They were testing it in SolidWorks, they were modeling it, they were looking at it. Somebody said, we can print it and find out for sure, and they did it. That's incredible. This story right here though, if you ask anybody in the 3D printing world, they will tell you this story is their absolute favorite story. And I cannot in any way make up the words I'm about to say, I'm not that creative. That he's holding is a ratcheting Allen wrench. NASA emailed that wrench to space. That is just my all-time favorite sentence to say out loud. These guys were on the space station and had a job they were working on. They didn't have the right size wrench to work on it. They did have a 3D printer on board that was being used for another experiment. They got some of the engineers at NASA in Houston to design the wrench they needed, emailed the file to this guy, Mark Kelly, up at the space station. He printed it on the printer and used that part to finish the job. That is just flat out awesome. It is awesome. What that means, and this right here, this story, illustrates everything that I want to do when I get out of the academic world. Think about what's happening right now at NASA. They have two major initiatives they're working on. First to go to the moon, and the second to go to Mars. So when you go to the moon, you don't know what you don't know. We've never really tried to be on it for an extended period of time. We can only guess at the things that they may or may not need. We can only guess at the parts that are actually going to break that they need to replace. We don't know. But what we do know is we have a limited amount of space and weight we can put up there. So instead of sending a bunch of parts that we think might break, what we can do is send a large amount of base material and an additive manufacturing platform. And they can 3D print any part they need, even things that we didn't imagine they might need when they're up there. What that means is every step forward, we can take an entire manufacturing process with us right there. Platforms to return home, repairs to a ship, repairs for medical devices that we didn't think we might need. Anything you can imagine that they might need on that planet, we can send basically the stem cell version of it in powdered metal, in plastics, in liquid resins. That is incredible. Not just incredible, that may be the difference in some of these guys making it home or not. That's unbelievable. The military also is very interested in it. And this is the heat exchanger I designed here. We actually put it right in the flow loop where the old one was. What we're working on here is determining a new type of fluid that the military wants to use as a coolant for some of their larger ships. What I've designed here has perfectly rectangular channels that are at 0.68 by 0.78 millimeters. There is no current form of manufacturing that could have made that in a single piece. What we found was these types of changes increase the heat flux. We can see now not just different geometries, we can go to circles, we can go to triangles, we can go to stars, whatever. Well, we can also have curved paths, spiraled paths, longer paths, stacked paths. We know the more surface area we get, the better heat transfer we get. If we only have this space, that's all the surface area we have available to us. But if we have a curved line for each of these paths that squiggles through here, we can double the surface area inside without changing the physical size. That's an incredibly powerful tool to have in your manufacturing, in your tool bag there. Size limitations are set. These things are going to go in a holder, in a machine. You can't fix that. But we can fix the geometries now inside it and work with that and see what else we can get. And this next one, this is a little near and dear to my heart. So when I'm done, if I forget to really, please ask me about the Enable program. It's one of the greatest things there is anywhere. It's just, it'll break your heart, and then it'll melt your heart when you get to help. It's just awesome. So like we talked about the Invisaligns, I have to be careful because this is a pretty, I care about this subject a lot. And this is actually part of the reason that I got involved in additive manufacturing. The reason that children don't generally get prosthetic devices or ones that fit well is because they cost tremendous amounts of money to make a custom prosthesis that fits you right. Children grow so fast that it's not economically feasible for most people. And it just generally isn't designed for children to begin with. A father started this program, this Enable program. He saw that he couldn't afford and couldn't find a way to get his daughter a prosthetic arm. He bought a 3D printing platform and worked it out himself and created that arm for his daughter. She has an arm that works the same. I mean, it attaches to her arm, it looks normal, she loves it. One of the things we actually learned is when you give children the opportunity to have a prosthesis device, they want to pick the color. That's awesome. So there's this program, Enable, where you can volunteer your time and your printer for children who can't afford or don't have access to a platform. There's pre-made templates, pre-made arms, hands, legs, a whole number of prostheses. Every summer I volunteer my time. It's cost me next to nothing. It's a $20 roll of filament. I go through, I make about 3 or 4. You can't imagine what that's worth. It's fantastic. You have the same problem with pets. And I know that not everybody's a dog person. I have dogs, I love dogs. I would do a lot for my dog. Prosthesis is extremely expensive for pets because most people don't do it. To be able to give your dog a way to walk again if he has a problem, to be able to give other people's dogs a way to walk again if we have a problem. And I recently learned when I took my dog to a vet in Friendship Heights that they are using 3D printed models to aid in surgeries they're doing on dogs' legs to help them. It's basically a woodworking jig that they can put over specific parts of the bone where they can measure exactly the cuts they're going to make it more precise. I'm working with them to hopefully maybe work out a way that we can help them with that and be involved in that also, because that's just awesome. I would do that for free. So, let's go back. Finally, here's the construction set. That's the machine I was talking about. It 3D prints the house. The last part, you have to take it out of the house. It 3D prints the roof. The only interaction required to complete the house is to use a crane to lift the printed roof up. When it's cured, put it on top of the house and you're ready to go. That is I want to say the last time I checked, it was a 48-hour job to complete the one-story house. Then another 12 to 15 hours to work with the roof once it's done. So realistically, you're looking at about 5 days tops to build a house with minimal human interaction. That's unbelievable. This is a artist rendering of what tract housing and low-income housing would look like using 3D printing. Laying down these rails, setting up the gantry, and having a couple of guys guide it. You're creating houses in rows, in weeks, instead of years. That costs next to nothing in labor, it costs next to nothing in parts, it costs next to nothing in time. That is a way we can get people homes that can't afford homes. So, a couple of things to think about here as we wrap it up this overview. What time is it?
1:26.
Sorry, I would talk about this all day, so you guys got to cut me off every once in a while. So, additive manufacturing is not going to be a replacement of mass manufacturing. That's not how it works. They serve two entirely different purposes. Mass manufacturing is not going anywhere. We cannot additively manufacture enough cars in a realistic way to outdo Ford. We can't additively manufacture realistically enough phones to outdo Apple. You're never going to out-Apple Apple. Apple's really good at it. They've been doing it a long time. That's not the market we're in. That's not how we have to think about it in additive manufacturing. There's a lot of platforms. There's a lot of ways to print. And within those platforms is variations of each one. You got to find the right tool for the job or it's going to work against you. It's like any other thing. If you use the wrong tool, you're already working too hard. These last two are two that I try to repeat to everybody I talk to because they're things that I have learned in my life. I'm quite a bit older than probably most of the people in this room. So I picked these up from some guys that I worked with a long time ago, and it has stuck with me forever because it was some of the most profound words I ever heard. Additive manufacturing represents a paradigm shift in the manufacturing world. What that means is we've got to stop thinking the way current manufacturers think. I worked with a guy named Eddie a long time ago. Eddie was super into automation in the late 90s and early 2000s when it was first becoming a real accessible thing. I said to him, that's really cool, we could speed up this machine we have with that, with what you're playing with. And he said to me, you gotta stop thinking about new technology in the old way. That's not the way you do it. Don't think, how can I do what we're already doing with new technology? Think about how I can use this new technology to do it in a new way. And what that means is, why am I going to try and out-Apple Apple, right? Because let's be real, Apple's business model is based on selling 10 million units of a phone before they become profitable. Why would I do that? When I can make one phone for one person that they specifically want, that's the color they want, has the features they want, is the size they want, fits in their exact hand, and still be profitable. Why am I going to make a million when I can make the one that people want? Why am I going to go out and make 10 million cars that look exactly like the Tesla when I can scan you and make a car that you fit in exactly? It's the size and shape and color of the car that you want, that you imagined in your head as a kid, that nobody else has anywhere. That's how you have to look at additive manufacturing. Not how can I do the thing we already do faster. How can I do something that nobody else has ever done and the one person in the world wants? That's the audience we're looking for with additive manufacturing. how can I do all the things we couldn't do before with this technology we didn't have before? Right. Questions? Right on. All right, so, yes, sir.
So the printer that you showed earlier with the, what was it called, SMA? With your experience, how usable are the parts that you prototype?
You know what, so far the ones that I've used are pretty strong because they're solid. You really can't hollow them out. So they're solid parts and they're isotropic because of the way they're fused. So they're same from all directions. Now, the resins we're using are fairly simple. So you can break them if you lean on them hard enough. But if you make a substantial part and you make it with a solid resin, it will go into a production line pretty easily.
And one other question. You mentioned being able to print with like varying density or varying tensile stress from
Yep.
the machine. Is that something you've tried or?
I have not yet. We actually have printed the dog bone shaped materials to put in the tensile machine, but we have not had time to go in there and really start pulling on them and see. We printed this dog bone shape from multiple angles, parallel, and then at an actual angle off the plate. So we're going to see if they're truly isotropic, but we just have not had the time to put them in the machine yet. Anything else? All right, let's take a little break, about probably 10-15 minutes. All right, we're going to talk a little bit now about file structure, preparing, exporting, and slicing files for print, and some best practices to give you the best chance of success. So no matter what print platform you're going to use, the workflow is always the same. We're going to create a 3D design and modeling software. We're going to export the design as an STL file. We're going to take that STL file and slice it in a slicing software. And then we're going to put that sliced STL file in the printer to print the geometry. What does change is the slicing software that we're going to use. That's printer specific. For our SLA printers, we're going to be using Chai 2-box. And for our FDM printers, we're going to be using Cura from Ultimaker. When we work on the metal printer, we'll be using a proprietary software called Magix. Today, in this section, we're going to focus on the two that are going to be most commonly available to you here at the UDC. That's our FDM and SLA printers. All right, there are many free versions of modeling software out there. They're all fine, whichever you're comfortable with. You can use OpenSCAD, you can use Tinkercad, any ones that are available, as long as the software is able to export files in an STL or an OBJ format. So the ones that are available here at the school, Creo PTC, Fusion 360, and SolidWorks. Creo PTC and Fusion 360 are available for free download for students. SolidWorks is considered the industry standard, and it is not available free for students, but we have a few licenses here in the modeling studio. If you have no modeling experience at all, a really good place to start is Tinkercad. It's a free 3D modeling platform online available from Autodesk. It has a lot of tutorial projects that it'll walk you through so you can kind of get the feel of modeling and how the workflow should go. When you start to get the thought process down so that you can look at solid shapes and turn them into the finished geometry that you want, then you can move up to the harder, more expert level software like Creo or Fusion or SolidWorks. It'll be an easy transition because the basic flow is the same, it's just a little more technical. Again, the software really doesn't matter as long as it has the ability to save or export files in STL or OBJ. So when you're designing for print, the #1 rule and the #1 failure of designing for print for new additive manufacturing students is designing in inches instead of millimeters. All designs for printers here at this school must be done in millimeters. Their slicing software and your printers only speak millimeters. When we design in inches, the slicing software will interpret that and will change the values of your print. If you have printed parts that are supposed to fit together, if you have tolerances set, or if you have a part that needs to have a specific size to fit in a geometry already decided on, this will create a problem. Always, always, always design in millimeters. Know which platform you're going to use before you begin designing. That way you can understand what the real pluses and minuses of that platform are and design to give yourself the best chance of success. When in doubt, read the instructions. Every single filament, resin, powder manufacturer provides specific information on how to get the best possible print out of their material. If you follow that as a guideline and then do a little experimenting and see how your specific printer responds to those settings, you can really dial in your printer to get the best use out of each of those filaments. Understand, different filaments, different resins, and different powders all will work differently in your printer. So you have to take the manufacturer's suggestions, try them, and then see what works best for you. Finally, Google is your friend. There is just a vast online community of people out there trying things and doing great work with additive manufacturing. The 3D printers and the designers out there on the internet are almost always happy to share their information. There's Facebook groups, there's Google Scholar documents, and YouTube videos galore. All you have to do is look for them. Think about checking with people who have done a thing you're trying to do before you just start leaping off the cliff. So some best practices for design. If at all possible, you want to create your model with at least one flat surface. This doesn't need to be particularly large, and it's not absolutely a necessity, but giving yourself at least one flat surface gives you the best way to adhere to the build plate. This will provide more solid adhesion to the build plate if you're using FDM or SLA, and that means your model is better equipped to make it through the entire print process with no issues. Always include any holes or cuts or cutouts that need to be in your design. You don't want to be cutting or drilling into a good print. It's never a good idea to try and put that kind of stress on a printed product when it's done. If you are planning to have interlocking parts or screw holes or slits for cameras, include that in your design before you print it. And remember, when you're doing that, FDM and SLA print materials expand after printing, meaning a designed 1mm hole prints at a much smaller diameter because the material expands when it's being printed. Plan for around 3% for FDM prints and 3 to 5% in SLA prints, and adjust your tolerances accordingly. Now that's a general rule of thumb. You'll need to try it out on your printer with the resin or the filament you intend to use. What I would suggest is if you are new to printing or you are using a new printer, there are plenty of calibration prints that are pre-made on Thingiverse. They will show you pre-designed holes, overhangs, and fittings, and you print one print and it shows you where the expansion is, how hard the overhangs will be before you have a problem, and how well things fit together. That's a really good guide to have when you're designing the rest of your parts. So we're going to be talking about exporting files now. Exporting files for STLs takes a little bit of work. You can't just do the standard default settings and expect to get the best possible print. We're going to focus right now on Creo because that's the software we mainly use here at UDC. So I'm going to show you here in a second on Creo exactly how to do it and exactly why you should do it. But before we get started, if you're saving a file in Creo, first save your file as a PRT, then go back and save a copy of that file as an STL. But before you click save, in the bottom right corner of the dialog box is a checkbox that says customize. Check that box, click save, and Creo will bring up an options window allowing you to adjust the cord height. That's what we're going to be focusing on, and that's where your best chance of success will come in. Okay, we've got a basic bearing here in Creo. We're going to see the real difference here on this one because it has some curves and edges and no edges. If you're making a solid square block with no curves, you're really not going to see a lot of difference from the default settings. But when you have rounded edges, curves, or details, you really need to adjust the cord height when you export your file as an STL. So what we're going to do here is we're going to take this file, save as, we're going to save a copy of it, and we're going to save it as an STL file. That's the stereolithography. And over here we're going to click the Customize Export button before we hit OK. Now you see we've got this extra menu here that we don't normally get, and if you mouse over the cord height, it'll tell you the values that you're able to use based on the model and your computer's ability. So we don't want to go all the way down to the bottom. There's a break-even point here. If we take the default settings like it is and hit apply, you can see here that it's converted our model into triangle shapes. But if you look here, if we zoom in on the curve itself, we've got sort of a pixelated curve. It's not really a curve. It's kind of hard edges. And if we look over here, we've only got 456 triangles that we've converted this image to. So what we're going to do, we're going to take this cord height from 2 down to 0.5. We're going to hit apply again. And you see now it's much smoother, the curve. We're still a little pixelated, but we've got a much rounder edge here. We've gone from 406 to 2,558 triangles. Now, there's going to be a break-even point, like I said. At a certain point, you're not going to get any more roundness that's discernible. You're just going to continue to add more data to the file. That's unnecessarily large file, may be bigger or hard to export from your computer. So work your way down until you get to the level of curve you're really looking for. And once you get to that point, go ahead and stop. So now that we've got that, let's go down just a little bit more. And there we go. Now you can see we've got a nice smooth edge here, or the roundness of the rounded edge is back. We've got a complete circle here, and that file is ready for export. So we're up to 11,000 triangles, and as you can see here, Creo has already exported it for us as PRT001 STL. Now that we've got that saved, let's talk about slicing. Slicing software is called that because that's exactly what it does. It takes your STL file and slices it into layers so that the print platform you're using can understand what it needs to do with the file you've given it. The slicer layers are determined by the layer height. And in the 3D printing world, layer height is what determines our resolution. There's a very simple maxim, no matter what printing platform you're using, and that's the smaller the layer height, the more the layers, the better the detail, the longer the print time. You can't really get around that. There's some things you can do on the plastic printers to speed it up just a little bit, but you run the risk of getting some failed prints when you do that. Now there's different slicers for each platform like we discussed earlier. We'll be using Cura for our FDM printers, we'll be using Chai 2Box for our SLA printers, and Magix for our DLMS printers. When you use Cura, you can download the free version from Ultimaker, but you need to add your printer's specifics into the program so that you get the correct G-code. you have to add your specific printer, its make and model, and you need to tell it what type of extruder you're using. If you're using a dual print head, if you're using a single large nozzle, and you need to let the nozzle size, let the software know the nozzle size. All of that will create the correct G-code so that your printer prints correctly the file that's been sliced. There's over 206 settings in Cura, but generally you only need to set a few of them. You need to set the nozzle temperature, the bed temperature, the layer height, the print speed, support settings, and the infill percentage. Now I don't have one listed there, but I will add, you also tend to want to add either a raft or a ring on your pre-print setup. When the nozzle temperature, bed temperature, and print speed are all going to be filament material specific. For instance, we generally print PLA somewhere between 206 to 210 on the nozzle temperature, and you want the bed temperature to be around 45 to 55 degrees. If you're printing ABS, you're going to want a print nozzle temperature of around 350 to 340 degrees and a bed temperature of around 55 to 65 degrees to help adhesion. Your infill percentage refers to how much of the build volume is solid versus how much is air. We make essentially hollow parts to save some print material and to save some time. Infill percentage refers to how much of the build volume is solid. So for example, if you print at 30%, 30% of the volume of your model will be solid material and 70% will be air. At 100%, the object will be completely solid. The general rule of thumb for infill is you never want to go below 30%, and you don't really need to go above 75% unless the material really needs to be strong. Let's look at Cura now. Okay, this is Cura. You can see here, Cura has already been set up for our printer that we have here, the Creality CR10S. When you download Cura for free, the first thing it makes you do is set up the printer that you'll be using. You need to set up the specific printer, the nozzle size, and the type of extruder you plan on using. If you're using a dual nozzle extruder, if you're using a high-end all metal hot end, you need to let the software know so that it can create the right file to give your printer the best chance of success. You see here, because we've already set it up for our printer, this ghost box shows us the volume that our printer has available to it. What we're going to do is bring in an object, the object we just made. See here, here's our bearing we just made. And see what happened here is it's dark and it's got lines across it. What that's telling us is this is well outside the build platform, and this printer won't be able to make that geometry correctly. So what we're going to have to do is go over here to the sizing option, and since we've got uniform scaling here, it doesn't matter which one of these we work with, they're going to snap together. So we're going to take this down to 75% and see if that'll fit it in our box, and it does. And if you look here, you can tell it's all the way inside the print area now because it's turned yellow. That lets us know that we're inside the print volume. If you look on the bottom, the red area is on the build platform, so we're ready to go here. Now we're going to tell it we don't need very much detail on this one, so we're going to take it up to 0.2 per layer height. Our infill is going to be 30%. That's our minimum. We don't need a particularly solid strength on this. And because there's no overhangs or outstretched areas, we don't need any support material for this particular geometry. Now, like I discussed before, if you go here to the custom area, you can see all of the extra settings. We tend not to use these unless you are an advanced user. If you understand and want to learn these, there's certainly various tutorials that will explain each of them to you. However, the vast majority of them don't generally need to be messed with unless you are doing very, very specific work. Because in this tutorial, this is a very basic tutorial, we're going to stick with the recommended settings. You can see here, it offers you the print quality items right here at the top, and we're going to go with what it is. So we've got everything we got set up. We've got it within the size. We're going to ask it to slice it for us. Now the slicing will take place. It'll cut it into the various layers, and we'll be able to actually see, right here you can see, this print will take 12 days, 10 hours, and 57 minutes. It will use about 4,446 grams of filament. Now that seems like a lot, and it certainly is a long time in real life, but recognize that the build volume for this particular printer is a little over a cubic foot. That means that this bearing would print at about a foot of diameter. That's a fairly large object. Now, what we can do here is export that file. You'll see it saves it in the G-code file format. Once we've saved it, we can actually take and open that file, and what it'll show us, if we open it with Notepad, okay, if we open the G-code file in a Notepad, we can see here that it's written in plain language. What you'll see here at the very beginning is the software it expects the printer to use, the type of printer you're going to be using this for, and then you'll see some code which tells the printer where to home its print volume, how to know which side is the end and what volume is available, and then you'll see these coordinates start. These are the path that the print head will take as it's printing your geometry. And it's just nothing more than Cartesian plane coordinates in very basic English. I'm not personally good enough at G-code to change anything in here. There are many people who have gotten into this aspect of the printing world and can help you with it, and it can help you do some pretty cool things. You can stop and pause prints in here in order to change colors. You can do some things that change the depth of the print from one resolution to another in various areas. I simply don't know enough to tell you how to get into that. If that's an area you're interested in doing some research on, you can find plenty of people who've done that type of work by Googling G-code and G-code exceptions. When we think about printing on SLA, we'll be using Chai 2 box. You can see it's very different than Cura. We have a much smaller print area, number one. The print area for the SLA printer we have here is about 4 inches by 2 inches by 7 inches. That is because of the way SLA printing works. The build volume is much smaller because SLA actually cures and adheres to the bottom of the tank as each layer is being formed. The print platform has to be able to overcome that adhesion each time it raises the platform up. So we have a much smaller print area in order to overcome that adhesion and be able to get a much smoother print. Now when it works the same, we open a file, we add the file to the printer, and again you can see that it's red. It's obviously entirely too big for our print area. So we're going to do the same thing. We're going to scale it down. Again, we've got the ratio locked, so that means they'll all work together. So let's start scaling it down until we get into a realistic size. So as you can see, as we get inside the print volume, it changes to blue. That lets us know how much is in and how much is out. Once we get inside the print volume here, the whole thing turns blue, and now we know we're on the print plate. Now, SLA does, instead of a G-code path, it does a series of images on an LCD screen which shine up from underneath onto the resin and cure it in a specific pattern. If at all possible, try to lay your object flat, because the taller the object, the longer the print time. In this case, we're able to get our bearing all the way on the platform horizontally instead of vertically. Now when it comes to SLA, we've actually really only got one setting that we need to change, and that's the setting for the layer height. Now with this one, you can see here, we're at 2 microns, 2.5 microns. That's the best resolution available to us on this printer. One interesting thing here in Chai 2 Box, if you set the correct dollar value per liter of your resin, the slicer will actually give you an accurate account of how much each part will cost you out of your resin bottle when you print it. Once your setting is correct, we come over here and we tell it to slice. As you know, as you can see, slicing in Chai 2 Box takes much longer than it does in Cura, because in Cura, the path is being created. We're figuring out how the print head needs to move in order to print the entire object. When we're slicing in Chai 2 Box, the software is actually creating a series of JPEG images for each image that the LCD screen needs to shine in order to cure the resin in that geometry. Now, that means two things. Number one, it takes much longer to slice the software, and number two, it takes much longer to save the sliced file, because the sliced file will be very large compared to G-code, because it's a series of images in exact order. Once we have the completed slice software, we'll save the file. It's a CDDB file. That file can be put on a thumb drive and put directly into the SLA printer.
I'll speak to this. So you want to just delete the whole line, right?
Yeah, don't even worry about it. And in fact, we're going to skip some of the warnings I gave about the metal printer, because that's not really relevant to to people who are going to be looking in general, unless they're here at the school.
We are going to put this on YouTube, though.
Yeah, but our warnings about our metal printer are specific to our room. If you had a metal printer available to you, they would tell you their procedure for it. So, and here you're not going to get to use it, so you would come to us and we'll use it anyway. Even I don't really get to, I mean, I do, but I really, I still have to ask, and I still have to go through the whole setup, so. Do we currently have a YouTube channel already, or are you building it? Right on. That's cool. They're trying to be like some of the other schools. NYC has one. Okay, as you can see here, we've got a fully sliced file now. It's going to tell us how long it's going to take. We're at 1 hour and 49 minutes. Like I said, it's telling me this is going to cost me about 50 cents of a resin. Also, it's going to tell me the volume I'm going to use in case maybe I'm running low and I need to know how to set that up. One interesting thing that it provides us here, this right now is showing us the slice layers at 0. If I click play here, it'll actually walk through each layer and show me what each layer will look like. And over here, you can see the print disappearing as each layer is used. Now, what this is showing us right here is exactly the image that will be shined through the LCD screen and cured the resin. That lets us know if we're looking for a specific layer to stop at, maybe to change the color, or if we're looking for specific issues maybe that we hadn't thought of ahead of time, we can really see how all of this is going to play out. This is a valuable tool to make sure that all of your geometry can print in the correct order. Once we've got everything set up, we'll save the file. As you can see, it'll be a CDDB file. We save it, and it'll take quite a while for this to write the file. That's because, again, this is a series of images being saved in a specific order. That's a very, very large file. In our presentation here, we've got some tables that will show you how exactly to set up FDM printers at temperatures for different materials to get the best possible print. And finally, a word about hollowing models in SLA printing. It's very difficult to print in SLA a hollowed model correctly the first time. There's a lot of tutorials on YouTube that can walk you through, but the basic idea is this. You're going to need to print a drain hole in the model. If you'll remember, when we discussed how SLA printing works, SLA prints happen below the liquid line in the reservoir tank. If you don't print a drain hole for the reservoir, what will happen is the object will finish printing below the liquid line. What that means is the inside of your object will be filled with liquid uncured resin. Excuse me. Your object will be full of the liquid, which will defeat the purpose because you'll still lose the resin you would have used in the print. What we've got to do inside Chai 2 box is an option to add a hole, and that drain hole needs to be on the side away from the print plate. So if we dig a hole in it, it needs to be about a 1/4 inch minimum in order to let the liquid out. We can say, okay, add a hole, and when we come down here, you can see now what I've got is a little dot that's going to be here. When I tell it where I want that dot to be, it's going to dig that hole out, and unfortunately this object isn't big enough for us to do that in. But what will happen is it'll dig the hole right there, which will be a drain hole, and it'll put the plug on the platform. When you're done printing, simply take the plug, fit it into the hole after you've shaken the liquid out, and you'll have a solid product again. This is a little bit hit and miss, and you really want to add your supports to your object before you dig the hole in it, because once it's hollow, Chai 2 box will try to fill the hollow section of the model with supports as well. And that will be very, very difficult, if not impossible, to remove from your printed product. So in conclusion, just remember, our workflow is always the same no matter what printer we're using. We design, we export an STL, we slice the STL file, and then we put it on the printer for printing. What changes is the slicing software we use and the best way to design the product. If you have questions, always read the instructions first. Check anything the manufacturer offers as best product and best use of their product, and best practices for printing with their product. And finally, never forget, Google is your friend. There's plenty of people out there who've probably tried at least what you're trying to do. Reach out to them, ask them for tips, ask them for what did and didn't work. Most of the 3D printing community is happy to share the knowledge they have. So once it's done printing, and this is, the reason these are red or orange is because this works on UV light, and this filters UV light out so you don't have extra light hitting here and crusting over the top layer of your tank. Once it's printed, we have to take the whole print plate off. Pull it out. Take it with a plastic scraper, remove it from the plate. We've gone through quite a few of these scrapers because you can see it's really on there. You don't really want to just manhandle it because you're going to mess up your print. It's still a little soft. Once it hops off, take it. Ordinarily what I would do, I didn't bring it up here because it's a small room. We'll take this print, we'll put it in an isopropyl alcohol bath. It's got to be 99% alcohol or better, or else you'll get water, and these things absorb a little bit of water when they're still drying. So once we've cleaned them off, it's not toxic, but you really don't want it on you because it stays on you for a while. Let's clean them up a little bit. And you can see what we've got here is a pretty good detailed model of the lamps. This print here took about 3.5 hours. And the final stage would be, right now what we're doing is the DIY cheap way, which is to take it and put it in the sun for about an hour after you print it. The real way, and the way we'll be doing very soon, is to take it and put it in a UV curing chamber, which is just a box with LED lights that shine at a specific wavelength. And once you do that for about 30-45 minutes after, that's completely cured and that's as mechanically strong as the part can get. So right now, since we're just printing toys, we don't really have to do that. But when we start printing parts that'll go into production work or something we might try to really use, that's the thing that gives us the best possible strength we can get out of that product. So, as you can see this one here, the various parts we talked about. Here's the print plate. It prints here hanging down. It goes all the way down into the liquid. You can see this is still liquid in here that's in here. If you look, if you remove this reservoir carefully, and right there is just an LCD screen, just like you have on your phone. And each one of those images shines up. Here, you can see underneath here, it's clear. And that image shines up through there, and wherever that is shining, that resin there cures and hardens. And it just continues over and over and over again as the plate comes up. With this printer, it works the opposite way. It goes from the bottom to the top, and you can see it goes here up and down and left and right. The platform actually moves also. So when you're printing with one of these, you don't want anything within the range of the platform all the way back and all the way forward. You don't want to hit it. Also, you don't want your hands anywhere near this area here. This is the hot end. It gets up to, like we said, 240 to 350 degrees. Also, these are, if you look at them, they're very thin and very tight. You don't really want to be touching any of the machinery. We can grind these stepper motor gears out with no effort, and those are about $140 a piece to replace. So realistically, once you click print, you should never have your hand anywhere here at all. And when you're setting up for print, the only thing you should really be touching is the build plate. And you can see whoever used it last didn't clean it. That's an important part of using these printers. When you're done, we have all the things you need right next to it. Windex, paper towels, not like those kind of paper towels, like from the bathroom. They don't leave lint. That's why we use them. Don't use soft anything. Don't use napkins. Use no lint paper towels and a little bit of Windex and clean this off. What this is here is also right next to the printer is a elementary school glue stick. You know, those old Elmer's glue sticks. I get the purple ones. They dry clear, but they're easy to see in purple when you do it. You don't need it for plastic. Plastic adheres to this glass with no extra effort. When you're doing something like ABS or nylon or one of those that don't have a lot of glue to them, you put down a layer of that glue on the bottom, and that helps the first layer support on the glass and hold, and then it will hold still during the rest of the print. Those are the little kind of things that we can walk you through when you're setting up your print, but they're the kind of things that you need to know to get successful prints. So if you're ready to start working in this world, do some design, look online. I'm going to email out the presentation I have here.
What's your opinion on printers and forks? What's your opinion on printers and forks?
Printers and forks.
The dude that scraped it with a fork.
Oh man. Okay, so let me say one last thing before. Thanks for reminding me. We lost a printer last year in Dr. Klein's lab because somebody who thinks they know went in there and took a metal object and gouged into the plate and popped it off and left a divot in the plate that looks like somebody hit a golf ball off it. That's worthless now. That entire printer is worthless because that person acted like they knew what they were doing and destroyed something that I need to use. I'm going to repair it. I'm not going to do it anytime soon. I'll do it when I get to it, when I'm not mad about it, which is probably going to be another month at least. So I don't mean to be, that guy, but number one, the school doesn't give us money. I fix most of these the way I can, duct tape and baling wire. Sometimes I spend money on it if I have to, but the school isn't fixing them. We haven't even put all the printers we have out because we know we put this one out and we had problems instantly. So what we're working towards is a way we can have all of these things available to us, but the people who know how to use them are running them. And so if you need them, then you go to those people and they help you set it up. If you need to use a printer, man, just ask me. I promise I'll help you. I promise I'll help you way easier than I'll talk to you if you break it. So it's just, these are expensive things, but they provide us with a great range of options. And the longer we keep them running, the better we have here. So that's really what it's about. Learn how they work, learn what they can do, and then let's get using them for the right stuff, the right way, without anything metal touching them. Any questions?
I just want to add that if you are not senior right now, if you're a mechanical engineering senior, major, when you move on to mechanical engineering capstone project, you are required to use any one of this 3D printer for your capstone project. So it's better to learn now, so by the time you become a senior, you are an expert. You don't need to ask for help.
Yeah, I get a lot of frantic calls right about this time of year from seniors who need to use these things. And look, man, I go to school too, so I'll help when I can, but it is what it is, right? So the better you know, the easier it is for us to help you, the better you can get access to them, right? All right. Good day. Enjoy. I'll send it out to everybody.